Okay, so today's unit that we're covering was unit 3, and this is exponential and logarithmic functions. So we're going to spend the first portion of our sheet dealing with exponential. And remember, this was a big modeling unit. We used a lot of word problems to model both growth, which looks like this, and decay, which looks like that. And it's exponential, which is why it has that curved shape like a hockey stick. So the two things we're going to define for, or try to find for every single problem that we're going through in this first section, are an initial value A that's going to show up once, and then we're going to find a base, or I'm going to write in a multiplier that we're going to multiply over and over and over and over again. That is why it's being raised to an exponent. So, for example, one, get a colony of bacteria. It triples in size every hour. If there are 100 bacteria to start, find the size of the population after 5 hours. So I look at this, I see, hey, we have 100 bacteria to start. This is my initial amount. This is what A is equal to. We also have this bacteria size that triples every hour. So we're multiplying by 3 every hour, so that base is going to be equal to 3. And if we want to write a function to kind of demonstrate what this looks like over time, we have a function. I'm going to use t as my input because we're using time, so f of t. And we're starting with that initial amount, 100. That only shows up once, but it's multiplied over and over and over again by this base 3. So I'm going to raise that to the t power, where t is my time in hours. Now, if I want to find my population after 5 hours, all I got to do is throw in a 5 here for my function, which means that we are just plugging that 5 in for t instead. And we can do that in Desmos real quick. Make sure you're using that NC test version. So I go 100 times 3 to the 5th power, and that gets me 24,300 is my ultimate population size as an answer. 24,300. So we also saw these problems with rates, where we were giving a rate as a percentage. When we get this, we first need to convert the rate to a decimal. Anytime you see a percentage, that should be a trigger, convert to a decimal. And then we need to add or subtract it from 1 to get a multiplier. Remember, we need to have numbers greater than 1 to get growth, less than 1 to get decay. So in this case, Ryan has 2550 in a savings account, and it pays 6.25% annual interest. We're trying to figure out how much money he has after 10 years. Our initial amount should be pretty easy. It should be this 2550, so that's going to be my A. However, this rate here is given as a percentage. So I'm just going to do some work here. Our rate is 6.25%. If I want to find that in decimal form, I need to divide it by 100. So I'm going to go 6.25 divided by 100, 0.0625. It's going to be that decimal form. And then so when we throw it in our function, we are going to want to add 1 to it. Let me write my function out real quick. Our function of time equals that initial value, that 2550, times, this is going to be 1.0625. Its growth, we are going to add 1 to it. And then what we want to do is we want to raise it to that t power. And then if we're plugging this in to find out how much money he has after 10 years, we can just simply plug in the f of 10, that 2550 times that nasty decimal, 1.0625, and that goes to the 10th power. I'm running out of space here. I apologize for that. I'll throw my $sign here, but let's throw this into Desmos and see what we get. We go 2550 times 1.0625 to the 10th. We get 4,675 and 52 cents. So 4,675, and I believe that was 52 cents. Now, going the other direction with a decay problem, we need to subtract it from 1 in this case when we go through that rate issue. So I can easily find this initial mass, which is 200 grams. That's going to be my A. When we're finding that rate, that thing we multiply by that base, we start with this 5%, rate equals 5%, but then we are converting it to a decimal. So I'm going to use Desmos again to make sure I get that right. 5 divided by 100, 0.05. And in this case, we want to subtract it from 1. So that base that we multiply by is 1 minus 0.05. We're starting with a whole. We're subtracting a little bit each time. So that gives us 0.95. And then we can write a function here. I'm going to scroll down just a little bit to give me some space. We can write a function here that maps that decay. So it's a function with time. We're starting with that 200 grams. We are multiplying by that 0.95 over and over and over again. That's a decimal there. That's a multiply there. And so that exponent is t to start, but then we can very quickly swap it out. We're calculating after 3 hours. So 200 times that 0.95 to the third power. And we can see how much is left here. 200, let me clear out some things. 200 times 0.95 to the third power. We get 171. And I'm just going to round this up to 5, 171.5. I didn't spec it in the problem, but that's all right. 171.5. So the final thing with this that was a little bit complicated is that the exponent may need to be adjusted depending on the context. We're going to write a function 3 ways. We're not actually going to plug anything in, but it's all going to start with this base idea. Considering a population of 100 people, for each scenario below, write a function that represents the number of people after t years. So our initial amount for all of these problems is going to be 100. So all 3 of these problems can start with P of t equals 100. P of t equals 100. P of t equals 100. Now, we're going to multiply all those initial amounts by a base. And in this case, that base is always going to be 2. It's doubling, it's doubling, it's doubling. Now this wording here, and on each of these is going to determine what that exponent is going to be. So t is in years. And so if we're doubling every year, then it's just pretty straightforward. We just raise it to the t power. However, if we're doubling 3 times per year, then we need to multiply that t by 3. So we are going 3t as our exponent. And lastly, if we're doubling every 3 years, that doubling is spread out over time, and specifically 3 years. So I'm not doubling until I hit year 3. So we need to take that t, divide it by 3 in terms of our exponents there. Okay, so exponentials covered half of our unit. The other half we dealt with logarithms. And logarithms are just ways to work with exponential problems and actually solve for the exponent. Remember that if we have an exponential form of base to an exponent equals n, then our logarithmic form just keeps that base low in terms of our log. The answer becomes the exponent, and then that answer to the exponential is what goes inside of our logarithm. They're used to undo exponents and answer the question, what power? So we evaluated these 2 different ways. We kind of thought about it as in more manual problems, we're able to kind of say, hey, take this base 2, raise it to some power question mark equals 8. 2 to the third power is what equals 8. And so my log base 2 of 8 is 3. Similarly, in example 6, when the log base isn't written, that tells us we have a base of 10. That's the common logarithm. If I have 10 to some power equals 1,000, Okay, that power that I need to have is 3. 10 to the third power equals 1,000. So in both cases here, our logs got evaluated to 3. For more complicated values, more complicated logarithms, like 640, base 640, and base 4, 3.5, we won't get a clean number, right? If we took 6 to the first power, we get 6, 6 to the second is 36, 6 to the third is 216. So our answer doesn't really show up there. That 40 doesn't really show up there. So we can just type this into Desmos to come up with it, because this is all programmed in. Log base 60, log base 6 of 40 is going to be 2.06. And log base 4 of 3.5 is going to be 0.90. It is very unlikely that we get asked a question just with this base idea of what a logarithm is. More often than not, we're going to be using these logarithms to solve some equations. So just like a lot of our other special solving, we want to start by isolating our expressions, and then we can kind of do our special step, which in this case is rewriting in logarithmic form. So I'm going to kind of bold that for you on your notes. So if I'm looking at this exponential equation here, the 2 to the k plus 6 power, it's already isolated. So I can jump right into step 2 here, which I'll write in blue, and start to work through this logarithmic form. So I have a log, my base is 2, inside of that is 6, and that is equal to whatever our exponent is, k plus 6. Now we could evaluate log base 2 of 6 if we wanted. Right now, log base 2 of 6. However, that gives us a really long, nasty decimal. So remember, we got in the practice of saving that until the very end, and subtracting 6 from both sides instead so that we could get k alone. And in this case, we have log base 2 of 6, and then we subtract that 6 to whatever that answer is. That's going to be what k is equal to. So if I plug that in, my log base 2 of 6 minus 6 will get negative 3.42, and that will be our answer there. We can save that rounding until the very, very end. Similarly, with example 10, we're going to need to use a logarithm to work with it. First, we got to isolate our expression, though. So isolate that exponential expression. I need to do that by adding 1 to both sides over here first. So now I have 2 times 4 to the x equals 128. And then I got to divide by 2 to get that 2 away and just have my base exponent pair. So now I just have 4 to the x equals 128 divided by 2 is 64. Now I have an instance where I can rewrite this as a logarithm. So I'm going to switch over to blue here. I have my log base 4 of 64 equals x. And that is clean and ready to go right there. So I'm going to plug that in, log base 4 of 64. And that gives me 3. You'll probably notice that, hey, you probably could have done that logarithm manually if you wanted to. But that helps us solve that equation there. So the other strategy we used to solve some of these exponential equations was by changing the base. And these are going to show up when we have an exponential on both sides of our equation. We have a 16 to the x here. We have a 2 to the x1, x plus 1 over here. Notice in the last two we did, we just had one side with an exponent. What we want to do is we want to start by rewriting the equation so that the bases are the same. You'll notice that we have 16 as one of the bases, 2 as another base. So what I want to try to do is I want to try to rewrite this 16 with a base of 2. And so if I do that, 16 2 to the fourth power would give me what 16 is. So let me just double check that in Desmos, make sure my math is right. 2 to the 4th power, that does equal 16. Okay, so we say that is a legal move to then do this. Instead of writing 16, I'm going to rewrite my entire equation. So blank x equals 2 to the x plus 1. And in that blank spot, I'm going to rewrite that 2 to the 4th power. Okay, haven't broken anything, rewrote it exactly the same, just changing that 16 to a base of 2. And then that gives me a problem where I can simplify these exponents of the power rule. I have 2 to the 4x equals 2 to the x plus 1. And hey, we now have a situation where my bases are exactly the same. The 2 and the 2 are exactly the same. So we can just equate these exponents together. We have 4x equals x plus 1. So now I can subtract an x, get all these like terms combined. I get 3x equals 1. And lastly, I can divide by 3. Let me scroll down a little bit. I can divide by 3 here and get x equals 1/3 as my answer. So I can do the same thing over here with example 12. Instead, here we have a base of 3 and a base of 27. So I'm going to kind of target this base of 27 and rewrite it as a base of 3. 27, if I wanted to rewrite that as a base of 3, I would need to go to the 3rd power. So 3 to the 3rd power equals 27. And then I can go through and rewrite my full equation, 3 to the 4x plus 1 equals, but instead of writing 27 there, what I'm going to do is I'm going to throw some parentheses, write my exponent of x minus 2, and instead of writing that 27, I'm going to write 3 to the 3rd power. After that, I noticed that my bases are the same, so what I can do is I can drop those bases. I get 4x plus 1 equals, and then we need to recognize that if we're dropping it in this step, that 3 needs to multiply with that x minus 2. So you can do that here, or you could have done it up top before dropping the exponent. Either way is fine. But then we need to distribute it and have the right side of our equation be 3x minus 6. The left side stays the same, 4x plus 1. And now we can move things over, combine like terms, minus 3x, get x plus 1 equals negative 6, and subtract 1 from both sides and get x equals negative 7. So if we forget how to solve these things algebraically, we can also fall back on solving them graphically. Remember, splitting our equation in half, plugging in Desmos as separate functions, and then locating the interceptions and those x values. So real quick, we're just going to do that for 10 and 11, confirm our understanding of that. So the left side of my equation for 10 is 2 times 4 to the x minus 1. So f of x equals 2 times 4 to the x minus 1. And the right side of my equation there is 127. So I plug that in, and I might need to zoom out quite a ways to hit this because I know that line here, that second equation, is going to be at 127. Zoom out, find that intersection. It looks like it's at an x value of 3. So that is indeed our answer. It didn't take me very long to find it just by graphing. For problem 11, we can also work through this by splitting our equation in two. We have a left side of the equation, 16 to the x power. That'll be what I throw up here, 16 to the x. And on the right side of our equation, we have this 2 to the x plus 1. You're going to notice as you type this in that when I try to hit the plus sign, boom, it kicks down off the exponent. So what we need to do is we need to make sure we're trapping that x plus 1 with parentheses in Desmos so it graphs it correctly. I'm going to home my screen so I can zoom back down. It looks like this intersection is a lot easier to see. It occurs at 0.333, which again is the same thing as 1/3. So we got the same answer there graphically. So last kind of concept that we want to hit with these exponential and logarithmic functions, these things are inverses, okay? So we can find them using those definitions of exponents and logarithms combined with our inverse rules that we reviewed yesterday. First thing I'm going to do is just kind of set up some housekeeping stuff. So I'm going to change that f of x to y. So we get y equals 5 times 4 to the 3x. And then I can swap that x and y in the equation. So x equals 5 times 4 to the 3y. Once I do that, I can solve for y, which is just isolating it. So I'm going to divide both sides by 5 to get that base alone. I get x over 5 equals that 4 to the 3y. Now I have a base exponent pair. I can rewrite this in logarithmic form. I get log base 4 of that x over 5 equals, 3y. And last thing I need to do is that kind of divide by 3 on both sides to get log alone. Sometimes we divide by 3 like that. This is going to look really messy. So the way I'm going to write it is I'm going to write it 1/3 times our logarithm instead of dividing by 3. So log base 4 of x over 5 equals that y. And so our final answer there, if we just change that y to our inverse symbol, is going to be 1/3 times log base 4 of x over 5. That one's a super complicated one. There's a couple of simpler ones in our problem set. This can also go the other direction. Going with example 14, where we start with a logarithm and we are going to kind of reverse that or inverse that to using an exponential. So a couple housekeeping steps, changing that f of x to y equals log base 3 of 5x, and now I'm going to switch that x and y in the equation. So x equals log base 3 of 5y. Now we can rewrite an exponential form because that log's all by itself. So I got 3 to the x power equals, not of log, 3 to the x power equals that 5y. And so I can divide by 5 here on both sides. Or we can view it as multiplying by 1/5 if you want. Either way is okay. I'll do that 1/5 again just to stay consistent. So 1 over 5 times 3 to the x power equals y. So that means that our inverse notation, inverse of x, is equal to 1/5 times 3 to the x. Now, one way to kind of check our work here is to throw these into Desmos. So if I throw my original function in, let's throw it in as y equals instead of f of x equals. So y equals 5 times 4 to the 3x. Okay, I get this graph here. And if I do this correctly, it should reflect over that line y equals x. I'm going to throw it as a quick dash here. And let's throw in our inverse, 1/3 log base 4. So y equals 1/3 times log base 4 of that x over 5. And we can see, yeah, it looks like a pretty good reflection. And actually, if I flip in my red equation, the locations of x and y, boom, those graphs line up perfectly with each other, and we accurately found our inverses.